Hey folks, we have already completed our introduction to hypothesis testing with z-tests, so now I want to introduce the t-test. So in this first video, it's just a light introduction to what the idea of a t-test is and a very important concept called degrees of freedom. Excuse me. So we've talked about hypothesis testing, right? Where we're trying to figure out the difference between a sample mean and a population mean, and whether or not that difference is large enough, given something that we know about variability or spread of the distributions, large enough that we would say it's unlikely to occur, right? Unlikely to occur more specifically due to chance occurrences, right? Chance forces on those effects, which means the independent variable has no effect on the dependent variable if chance is what's likely operating, right? It means that we can have that difference be this far, this far, this far, reasonably far, but still pretty close to what we would expect to be normal variability. That's that whole center of the middle of the distribution. All of what we expect to happen, the likely, probable events. It's when we get way out into the tails of the distribution where there's such a small little section under the curve that percentage is so tiny, 5% or lower, right, with our p equals 0.05, that we say that it's unlikely to be due to chance, and then we reject the null because the null basically says chance is the only thing occurring, right? Your independent variable does not affect your dependent variable. We reject that null in that case, and we say that we have found a statistically significant difference. We have found a difference that supports our research hypothesis. So we said that cutoff value that determines where the 5% or 2.5% in each tail happens to be, is calculated because we used in behavioral sciences a p-value of 0.05. We say that it's an acceptable risk that we would be wrong 5 out of 100 times when we reject the null, because that's an okay acceptable risk in behavioral sciences that's sort of been determined by the field over time. But it's entirely possible that you might be, let's say, even less conservative, and you're willing to take a 1 in 10 chance, a 10 in 100 chance, a p-value of 0.10 instead of a p-value of 0.05. In this case, we have to look up a cutoff value that corresponds to 10% of the distribution being in the tail. We also discussed directionality of hypotheses. So if I say that group X or sample X will be greater than the population mean, well, then I'm specifically predicting one direction of the effect, that the sample mean will be higher than the population mean. Not merely that it will be different. Different says it could be lower or it could be higher. If I say different, then I'm doing what's called a non-directional hypothesis. If I say that one will be greater than, faster than, right, we posit a particular direction, then we have what is clearly called a directional hypothesis. Why does this matter? Well, it matters because if we have a non-directional hypothesis, it's saying that we could expect our sample mean to come in above the population mean, in which case our z statistic or our t statistic, as we'll see soon, would be a positive number. But if we would expect it to become below the mean, then because of the way the equation is set up, we would expect then our test statistic to be a negative value. And so we have to have cutoff scores that are on both sides of the distribution. Non-directional tests, two-tailed tests. That would mean our 5% or our 10% or whatever p-value we are using has to be divided in two so that the 5% has 2.5% in each tail. Okay, a one-tailed test would be simply saying a particular direction. So if we say the sample mean is going to be higher than the population mean, we're expecting it to be in the positive direction, right? One score minus the other score should be a positive value, and that would give us positive z statistics. And so our 5% cutoff needs to be all the way over into that positive end, right? And so this is how we would use that sort of information to look into our table to figure out what our cutoff values are. So why did we go through all this? Well, hypothesis testing allows us to say something about two populations, or maybe more populations, depending on the test that we're using, saying whether or not population A is the same as population B. Does it come from the same larger population, or is it possible that our sample that we're looking at is different from that larger population? It's different. It instead corresponds to a different population, a population of people who did get training before they went out and did that particular task versus a population of people who didn't get the training. These people should have greater performance, and if we determine there to be statistically significant differences between the groups, we're rejecting the null and we're saying that we can now conclude something about this larger population of people and what they look like when they get training. Whole goal, again, estimating something about the population. Now, in the z-test that we've discussed so far, we didn't really have to estimate a whole lot about the primary population, the larger population, because we already were told a lot about that population, right? We were told the population mean, mu, and the population standard deviation, that little lowercase sigma that's down there. But what if we didn't know that much about the population? What if I wanted to know whether or not my sample was different from the population, but I didn't know the population standard deviation? Maybe I just know the mean because I know what it really should be like, right? I know what the average of the population should be. It's okay if it's a little bit above or a little bit below. I want to know whether or not my sample differs considerably from that population. That's really where we get the t-test, okay? And it's called the t-test because of a guy named William Gossett. Yeah, I know that doesn't make a whole lot of sense, but I'll explain that in a minute. Gossett was working at Guinness, and he was put in charge of quality control, right? And so the cool part about quality control at a brewery is that it means you get to go around and drink a lot of beer. The cons, of course, are that if you drink full pints from every batch that comes out and every barrel and you'd get rather intoxicated rather quickly, and then your ratings of quality would no longer be reliable, right? And so what Gossett found was that in order to take some estimate of the population, right? He didn't know what the variability was of the taste of Guinness, the quality of Guinness, across the whole population of all the Guinness that's ever made. And he couldn't go and sample every single batch, every single barrel, because there's just far too many of them. Even without being intoxicated, it would simply take way too much time, right? And so one of the things that he developed was this idea of sampling, right? And this led to sort of the central limit theorem and the idea that if we took a decent enough size sample, then we could conclude some things about the population, right? Because basically the comparison distribution, the distribution of means, would be normal. And so we could see where our sample mean lied within all of that. Well, Gossett basically did the same thing here and said that if we don't know all that about the population, for example, we know the mean, we know what the average Guinness should taste like. We don't know how far it's spread. We can use our sample to estimate the variability of the population, right? So we can use sample variability to estimate population variability. So in comes student's T. Now the reason it's called student's T, I'll show you a copy of the paper later, is because he had to publish this under a pseudonym because Guinness refused to allow its scientists to publish any of the work that they had developed while employees of Guinness, right? Guinness didn't want one of their neighboring breweries, competitors, to get wind of Gossett's work and then outcompete them to the same product, right? And so he did still publish it because he thought it was valuable, and he did so under the name A Student. And therefore, we've known this test moving forward as student's test, student's t-test, okay? So how do we estimate population variability with sample data? We have to know that there is some error in sampling, right? It's not the whole population. In fact, one of the primary errors that we see is that with smaller samples, we have less and less spread, right? So look at the crowd in the that are running these two groups, right? When you have only 4 or 5 individuals running together, they tend to be fairly close to one another. When you've got a huge group running the marathon, well, then they have to be functionally more spread out. That's not exactly the same force that causes samples to vary in their spread or variability, but it's a good analogy. In essence, when our samples are small, we're far less likely to have very many extreme scores, right? Those extreme scores are really rare. When our samples are larger, we're going to start to pick up on some of those extreme scores. And so in order for us to try and estimate population variability, population spread, we have to look first at sample variability and how to account for this error. So larger samples should be more spread out and better representing population variability. Smaller samples will have more error, be less spread out, and be worse at estimating population variability. So what we're going to do is take our equation for standard deviation. So this is our equation for standard deviation, except I've tweaked it. And some of you read ahead or looked online and you already used this formula accidentally in the past. Notice the denominator now, instead of dividing the sums of squares by n, we're dividing the sums of squares by n minus 1. Right, so sample size minus 1, which means if you had a really, really big sample size, 1,000, right, or 65, as I point out down below, subtracting just 1 off of that is a very, very minor change to that denominator. It doesn't have a large effect then on the estimate of variability. That's because larger samples are already closer to estimating population variability, so they require less of a correction. Smaller samples, an n of 4, for example, if you took 1 away from that, you've changed that value by quite a bit, right? A change of 25%. That'll have a larger effect on standard deviation. And thus, this new measure of standard deviation that we use for samples, right, not for populations, for samples, uses the n minus 1 in the denominator to account for that error. All right, so we're going to be using this now anytime we talk about sample data, and we're estimating sample standard deviation, okay? Now, remember that we were talking about not right? We were talking about standard error for z-tests because we said the variability of the distribution of means is going to be smaller than the variability of raw scores because means, averages, will be less extreme than the raw scores that contributed to those various averages. And so what we did there was to take the standard deviation, the population standard deviation, and we divided by the sample size in order to calculate standard error for our z-tests. Well, we don't know population standard deviation. Instead, we know sample standard deviation. That's already been corrected, right? Divided by n minus 1. But we still need a measure of standard error, not standard deviation. And so we simply take the s that I just showed you how to calculate, and we divide again by the square root of n, right? So just like before, when you get standard deviation to standard error, you simply take that standard deviation and you divide by the square root of n. We're just doing it now using the sample standard deviation, not the population standard deviation. Try to make sure you don't do standard deviation divided by the square root of n minus 1 here, right? That's an easy mistake to make because you're new to the n minus 1 in the denominator. We already did that, though, when we calculated standard deviation. We don't need to do it again here, right? That would be an overcorrection. It would be incorrect. Okay, so let's look at the formula for students T. Now, first, you should already notice that this looks a lot like a z formula. Z was equal to sample mean minus population mean divided by standard error. This T formula right here is sample mean minus population mean divided by standard error. The only difference is that because we don't know population variability, we have to estimate it using sample standard deviation, sample variability. Right? In essence, it tells us the same thing. It's in standard error units, right? And so a t statistic tells us how many t's, or how many standard error units, that sample mean is above or below a population mean. Now let me point something out here. We had to calculate our variability using sampled data. And I talked about how larger samples are going to be more likely to represent the population better than smaller samples will. In fact, if you look at your t-table with all these values, and we're not even going to really use it until the next video, but if you looked ahead and you scanned across the sample size and the degrees of freedom, concept I'll introduce here, along the far left column, you'd see that down at the bottom, after about a sample size of 30, it just gives the symbol of infinite, right? It gives you the values. Now, what it's trying to say is that the z statistic, the z table, that is based on population values. That's unchanging, right? Unchanging because the population size is this constant, very, very large infinite size, right? However, the t-table is based on sample data. And the sample data, the distribution of all those sample means, is going to change its variability as a function of sample size. When you have very, very small sample size, like a sample size of only 3 individuals, right? In that case, that distribution, that t distribution, is very, very spread out. As you increase sample size, you can see the t distribution becomes less flat and starts to approach a normal distribution. And in fact, as you can see in this figure, the bar for the red t distribution at 30 degrees of freedom is nearly identical now to the purple bar that represented the normal z distribution. So what this means is that when your degrees of freedom are greater than 30, you are working with essentially values that you would find on the z table, right? The z distribution, of course, is unchanging, right? The shape of that is always perfectly normal, perfectly peaked as it is. The t-distribution, while normal, changes how spread out or peaked it is as a function then of sample size. And I told you I'd show you students' test, or students' paper. There it is, the probable error of a mean by student. Right, so students' t. Now, the t-tests can really be used anytime we want to see if a sample is different from a population, which means we could say, is one sample different from a known value of a population? So if I know something about the population already, can I say whether my sample does or does not fit in that population? How about if I had two different samples? Let's say I had some people take caffeine and other people did not get caffeine, got water, and then both of them had to run the mile or take a memory test. They're very different people. They're independent of one another, and their performance is not connected in any way to each other. And so we call this an independent samples, right? And what we'd be asking is, are these two samples from the same population, or are they from different populations? That is, did caffeine change people such that they are now behaving like a group of individuals under caffeine, and the individuals without caffeine are behaving like people who are not under caffeine, and that these distributions are far enough apart that they are in fact different populations, different groups of individuals, right? We can also just have somebody perform a test. So maybe I see how quickly you can solve a puzzle. And then I give you training on how to solve similar puzzles. And then I give you the puzzle again and measure how quickly you can solve that puzzle, right? If I show an increase, perhaps I can say that my training improved your performance in problem solving. In this case, it's the same people, right? These folks are being measured 2 times in order to create our 2 conditions, and we would call this a paired or dependent samples test. Dependent because however I perform the first time, that should still be related to how I perform the second time. Even if training improves me, it'll improve me from where I was before to where I am after, right? Those 2 measurements are dependent upon one another. They are not independent. Excuse me. So let's talk about this n-1. Why do we do it? Well, I've told you it's because we're trying to account for variability, right, and the difference in variability between samples and populations. But there's also something more to this value. It's referred to as degrees of freedom. And degrees of freedom are necessary whenever we make an estimate of something. So we're largely estimating mean values, right? And so when you add a number of scores into a sum to divide by the number of scores to get a mean, how many of those scores, those raw scores, can take on any value at all? They're free to vary, right? Those are the degrees of freedom. So look at the example down below. Let's say I ask 6 people how often they floss their teeth, and I record their average, okay? So just look at the first 5 values there on the left. 3, 5, 1, 0, and 2, okay? Now, if I know that the average is a 2, right? So that the average times per week that they floss is a 2, then even if I didn't know that last value to be 1, I could figure it out, because I know that if the average is 2 and there's 6 scores, well then something divided by 6 gave me 2, right? So 12 divided by 6 gave me 2, and then I could figure out what that last one had to be to get me to that sum of 12, right? So really, 5 of those scores could be anything at all. I could change them completely, right? So it could be 2, 1, 0, 0, 0. If my average is still 2, and those are my raw scores, right? Those 5 scores took on completely different values this time. They were free to vary. Then that last one still has to be fixed, right? In this case, it would have to be a 9 in order to get my sum high enough that it would get all the way to 12 so that we could divide by 6 and still end up with the average of 2. So this example is trying to illustrate how degrees of freedom works when estimating the mean. We're essentially saying that if you had 30 scores contributing to your estimate of the mean, 29 of them could be anything at all, but that 30th one would have to be fixed, which means you would have 29 degrees of freedom for that particular estimate. So that's kind of important. Let's watch another quick video that we'll use a sort of baseball analogy and then relate it to estimating the mean. Hopefully that'll really hammer it home, because degrees of freedom is an important concept and not always the easiest to understand on the first presentation. Okay, so let's watch this video.
When I tell people that we use n-1 in the denominator for estimating population standard deviation, many people want to know why. This video will explain the mathematics behind why we use n-1 and what we mean by degrees of freedom. The degrees of freedom refer to how many options exist for variation in our data. Specifically, it means degrees of freedom to vary. Let me illustrate using an example of making choices when choosing positions for a softball team. Degrees of freedom will refer to the number of people who get to make a choice. There are 9 positions on the softball team: pitcher, catcher, shortstop, first base, etc. And there are 9 of us. We draw straws to see who gets to go first. The first person picks a position to play on the team. The second person chooses from among the remaining 8 positions. The third person chooses from among the 7 remaining positions, and so on. Each person gets to choose a position. But who does not get a choice? When we get to the 8th person, that person chooses between 2 remaining positions. But the last person is stuck with whatever position remains, so that person doesn't actually get to make a choice. When choosing among 9 positions, only 8 people get to actually choose. The last person's choice is chosen for him, based upon the choices of others. You have n-1 choices, or degrees of freedom to choose. Now let's apply this to a sample. We have chosen a sample of 9 subjects from an unknown population. The mean of our sample equals 5. What do you estimate will be the mean of the population? Because the sample mean is the best estimate of the population mean, we estimate that the mean of the population will be 5. So what is the formula for the mean? The mean is the sum of x divided by n, which we estimate must equal 5. So we are now going to select 9 new scores from this population with an estimated mean of 5. The sum of x divided by 9 equals 5. So what is the sum of x? It has to be 45, because 45 is the only number that can be divided by 9, our sample size, to equal the mean of 5. The values in the population can vary, but they must still average to the mean. We have chosen our 9 people, and we know that their scores have to add up to 45 so that we get that mean of 5. Well, let's see what their scores were. If you like, get out your calculator and enter a value of 45. As we see the numbers from our sample, subtract them from 45. The first person got a 5. That leaves us with 40. The second person got a 6. That leaves us with 34. The third person got a 4. That leaves us with 30. Next is 5. That leaves us with 25. Next is 4. Leaves us with 21. Ooh, the next one's a 7. That brings us down to 14. Next is 3. That leaves us with 11. And the next to last person got a 5. We only have one more person left. What does his score have to be? The last one has to be a 6. You can vary any or all of the population values, n, but the last value, n-1, will always be defined for you. You have n-1 degrees of freedom to vary. Population estimates using n tend to underestimate the true population values. So n-1 is a corrective factor.
Okay, so now let's wrap it up, talk about these one-tailed, two-tailed tests again, with a sort of funny example, and then we'll move into calculating t-tests, okay? So, a tale of two tails and pizza. Suppose a pizza place near your house has crafted a new style of pizza, and they want to know how their customers like it. They randomly select 40 customers from their database and send them each both a new style and old style pizza with simple instructions to provide a rating of -10, strongly favoring the old style, to +10, strongly favoring the new style. Okay, we don't know what they're predicting here. Let's say we have one employee who comes up and he says, I think the new pizza is a hit. Maybe that employee invented the new pizza, decided the toppings or something like that. I think it'll be so popular that it will in fact be higher than the old pizza. And so we would expect then ratings to be positive, right? We'd expect them to end up near the plus 10 values of things, right? This particular individual is predicting a directional effect because they're saying the new pizza will be better than the old pizza, and thus we'll have these positive values, right? Let's say another employee has the opposite prediction. He doesn't like this guy's new pizza. He says, your pizza sucks. The old one was better, and I think people are going to rate it as such. And therefore, I predict that the old pizza will be liked more so than the new pizza. Well, based on our rating system, that would end up with negative values. These two directional tests predict either one direction or the other direction of the effect, right? These are what we would call one-tail tests as well, right? And so I'll show you an example of the distribution here in a second. But let's say instead the boss comes out and he says, hey, I like both pizzas. I'm pretty sure people will like them differently, yes, but I don't know honestly which one they're going to prefer. Some people might prefer the old and some people might prefer the new. So I'm going to make a prediction that they'll be different, but I don't know in what direction they will be different, right? This is then obviously a non-directional hypothesis, and we're saying that, well, it could be that we'd have negative values, it could be that we'd have positive values, and so we really have to look at both ends of the distribution. We need to look at a two-tailed test, right? So if I'm predicting that the new pizza is better than the old pizza, and I'm going to get positive values, then when I calculate my test statistic, a Z or a T or whatever test statistic I'm calculating for my example, I'm expecting those to be a positive test statistics, right? Let's say a T of 2.3 or a Z of 4.0 or whatever it is. I'm expecting it to be over on the positive values. So my 5% cutoff is going to be a positive cutoff value. If I predicted that the old pizza was going to be better, then I'm predicting negative values, and my 5% cutoff is going to be for a negative value, right? A negative cutoff score. And if it's a directional test, then my 5% is not in one tail, it's in two tails. And so it has to be 2.5% in each tail. If I do 5 in each tail, then I've bumped it up to a 10% chance of type 1 error, and that's not where we want to be. We still want to stay at 5%. So you divide it 2.5 into each tail, and you look to see whether or not your test statistic exceeds either that positive cutoff or that negative cutoff. All right, so hopefully this kind of cleared up some stuff that we were covering in the Z-statistic and Z-test lecture, and helps you get ready for calculating now the T-test, because that's where we're going next, all right? Cheers.